Welcome back to another deep dive. We spend our entire lives just walking around on this planet, building our cities, driving our cars, and we assume the ground beneath our feet is this permanent, unshakable thing. We really take it for granted.
Solid as a rock, as they say.
Exactly. But then, every once in a while, the curtain slips, a volcano just erupts, spewing liquid rock that's been cooking miles and miles beneath us.
Where the ground itself ripples like water.
Yes. And it topples buildings in seconds that took years to build. It's terrifying, absolutely. But it's also this huge wake-up call. It tells us that what we're standing on isn't just rock, it's a lid.
It's a lid on an engine that has been running for, 4.5 billion years? It's the ultimate dynamic system. We see the scenery, the mountains, the oceans, but we rarely think about the machinery that actually built it all.
And the most frustrating part, I think, for a scientist, or even just for us, is that we can't see the engine room. We're locked out.
That's a great analogy. It's forensic geology. We're trying to reconstruct a scene where all the evidence is buried under thousands of kilometers of rock and unimaginable pressure.
Forensic geology, I love that. And that is exactly the mystery we're decoding today. I mean, if we can't dig a hole deeper than just a few paltry kilometers, and we'll get to how paltry in a minute, how on earth do we know with any certainty what's happening 6,000 kilometers down?
It turns out it's a massive detective story. It really is. It involves physics, geometry, and, well, it's like deducing the contents of a locked room without ever opening the door.
Fantastic. Now, before we start cracking this case, I just want to give a massive welcome to everyone tuning in. This isn't just any discussion. This deep dive has been specially curated for the Simplified UPSC by PPP community.
That's right. Whether you're a serious aspirant, a lifelong learner, or just someone who wants to understand the physics of our planet, you are absolutely in the right place.
We're going to be covering the fundamentals from the NCERT Class 11 Physical Geography book, specifically Chapter 3, Interior of the Earth.
But, and this is important, we're not just summarizing the book. We're going to connect those static facts to the kind of high-level analysis you need for the Civil Services Mains.
Precisely. We're bridging that gap between just knowing the fact and actually using the fact. And hey, if you're finding value in this, and I really hope you are, I have a humble request.
Go on.
Please take a moment to subscribe to the Simplified UPSC by PPP YouTube channel. It honestly helps so much with retention, and it ensures we can keep making these deep dives for you.
It really does make a difference. And if you're in a position to, please consider supporting us on Patreon. That support is what's truly vital to keep the lights on and the research coming.
It is. And on that note, we have to give a warm shout out to all of our current supporters. You guys are the bedrock pun fully intended of this whole project.
We couldn't do it without you. Your contributions allow us to put the time in to make these as comprehensive as they are.
Absolutely. Also, you know the drill. Don't forget to like the video and share your valuable comments. We do read them. And for the serious students listening, we've got you covered.
We do. We have free notes with practice previous year questions, PYQs available on our public Telegram channel.
But if you want the full experience, like access to all the videos in this series at once, plus the premium notes, that's where you need to be.
And the premium notes are a whole other level. We're talking detailed breakdowns, extra PYQs, and model mains answers. To get all that, you just need to join the private Telegram library.
How do they do that?
Simple. Just send a DM to us on the public Telegram channel, and we'll get you set up in the private library. It's a game changer for structured revision.
Okay, housekeeping done. Let's unpack the Earth. Our mission is to decode Chapter 3. But let's start with the problem of scale, because I think most of us have a really hard time visualizing just how big this planet is.
It's almost impossible to comprehend. We see a 12-kilometer hole and think, wow, that's incredibly deep. And for us, it is. But for the planet, it's nothing.
So give us the numbers.
Okay. The radius of the Earth, so the distance from where you're sitting right now to the dead center of the core, is approximately 6,370 kilometers.
6,370. Okay, that's our target distance.
That's the journey. Now, let's consider our best efforts to physically go down there. The deepest gold mines in the world, the ones in South Africa, they only go down about 3 to 4 kilometers.
That's it. 4 kilometers out of over 6,000.
That's it. And even at that depth, the conditions are just hellish. The temperature rises so rapidly, it's what we call the geothermal gradient, that going any deeper becomes technically impossible.
It just gets too hot.
Way too hot. The rocks themselves are scorching, humans can't survive, and even the heavy machinery starts to fail.
Wow. Okay, so mining is out. We hit a heat wall pretty fast. What about dedicated scientific drilling? I know there have been these massive projects like the Deep Ocean Drilling Project or the Integrated Ocean Drilling Project. Surely we've done better than a gold mine.
We have, but not by much. The world champion of deep drilling is the Kola super deep borehole. It's in the Arctic Ocean. The Soviets drilled it for decades, pushing technology to its absolute limit.
Okay, the moment of truth. How deep did they get?
About 12 kilometers.
12.
Just 12. To put that in perspective, if you imagine the Earth as an apple in your hand,
Okay, I have an apple.
the deepest hole humanity has ever drilled hasn't even fully pierced the skin of that apple. We've barely made a scratch.
That's incredibly humbling. It really puts our technological arrogance in check, doesn't it?
It does.
So direct observation, actually seeing and touching the deep Earth, is basically off the table.
Yeah.
But what about volcanoes? I mean, they're kind of nature's drilling rigs, aren't they? They bring samples up to us.
They do, and that's a crucial direct source. When a volcano erupts, it throws out magma, which is essentially molten rock from the interior. We can take that magma, let it cool into rock, take it to a lab, and analyze its chemical composition. It's a direct sample.
We feel a butt coming.
There's a big catch. We know what the material is, but we don't know for sure where it came from.
It doesn't have a return address.
Exactly. The magma chamber that fed the eruption could be 50 kilometers down or it could be 150 kilometers down. We can't be certain. So while it tells us there's molten rock down there and gives us clues about its chemistry, it's hard to use it to map the layers precisely by depth.
Okay, so we can't dig down, and the stuff coming up is ambiguous. We have to turn to the indirect sources. This is where the physics comes in, right? The detective work.
This is the forensic part. The first set of clues are basic properties of matter: temperature, pressure, and density.
Right. We know from mining that temperature increases with depth.
And we know pressure increases simply because of the immense weight of all the overlying rocks. It's like diving in an ocean, but the ocean is made of solid rock thousands of kilometers deep.
The pressure must be astronomical.
It is. And because of that immense pressure, the material gets squeezed, so the density has to increase as you go towards the center. So physicists can build a model. We know the total mass of the Earth.
How do we know that?
From planetary mechanics. How the Earth's gravity affects the moon and the sun affects the Earth. We can calculate its mass very accurately, and we know its volume, so we can calculate the average density of the whole planet.
Okay, and what does that tell us?
Well, this is where it gets interesting. The average density of the rocks on the surface, the stuff we can actually pick up and measure, is about 2.7 to 3 grams per cubic centimeter.
Okay, 3 GC meter.
But the average density of the entire Earth, based on its mass and volume, is about 5.5 grams per cubic centimeter.
Wait, hold on. If the stuff on the surface is only 3, and the average for the whole planet is 5.5, that means the stuff in the middle must be incredibly heavy to pull that average up.
Precisely. To get that average, the math tells us the core's density has to be somewhere around 11 to 13 grams per cubic centimeter. It's hugely dense. So even without seeing it, the physics tells us the core is made of something very, very heavy.
Okay, hold that thought on the heavy core. I saw meteors listed as an indirect source, which seems kind of random. How does a rock falling from outer space tell us anything about the inside of our planet?
It's a brilliant piece of logic, actually. The basic assumption is that meteors and the Earth are siblings. They were all formed from the same primordial cloud of gas and dust, the solar nebula, at roughly the same time.
So they're made of the same starter dough, so to speak.
Exactly. They share the same elemental DNA. Now, many meteors we find are fragments of larger planetesimals that formed and then got smashed apart. When we find a metallic meteor, basically a big chunk of solid iron and nickel, we think we're looking at the raw material of a planetary core.
So if we see meteors made of iron and nickel, it's a good bet that Earth has a massive stash of iron and nickel too.
Correct. And since iron is very heavy, during Earth's early molten phase, it would have sunk straight to the center due to gravity. This aligns perfectly with our density calculations that demand a super heavy core.
That is some real Sherlock Holmes stuff right there. It all fits. Now, what about gravity itself? I think most of us assume gravity is just constant, 9.8 meters per second squared, done.
A very common misconception. Gravity is not constant across the globe. We have what are called gravity anomalies.
Define that for us.
Well, first, just because of the Earth's shape, it's slightly flattened at the poles. You're physically closer to the center of mass at the poles, so gravity is a bit stronger there than at the equator. But it's more than that.
It varies based on what's underground.
Exactly. The gravity you feel is influenced by the mass of the material directly beneath you. If you're standing over a massive, dense deposit of iron ore, the gravity reading will be slightly higher than expected. That's a positive anomaly.
And if you're over something lighter, like a big salt dome,
Yeah.
it would be lower.
A negative anomaly. Exactly. So a gravity map is kind of like an X-ray of the density variations in the crust.
That's fascinating. And magnetic surveys do the same thing, but for magnetic materials.
Yep. They reveal the distribution of magnetic materials in the crust. But all of these things, density, meteors, gravity, they give us great clues about the crust and the general composition. To really see the layers, to map the structure deep down, you need something that can travel through the Earth.
We need a planetary ultrasound.
We need earthquakes.
And that brings us right to section 2. Earthquakes. This is really the heavy lifter in the NCERT text, isn't it?
It's the most important tool we have. An earthquake is fundamentally the planet speaking to us in a language we can measure.
So let's start with the basics. Why does the ground shake? What is an earthquake?
It all comes down to a release of energy. The Earth's outer shell, the lithosphere, isn't one solid piece. It's broken into these massive plates that are always moving.
But they get stuck at the edges?
They do. The edges are just rough rock grinding against rough rock. So they get stuck, but the force driving them continues to build. Think of bending a dry stick. You apply force, it bends, and all that potential energy is stored in the wood.
Until it can't take any more.
And then, snap. That snap is the earthquake. All that stored potential energy is instantly released as kinetic energy.
In the form of waves.
In the form of seismic waves that radiate out in all directions from the point of the snap.
And that point of the snap, deep underground, that's the focus.
Yes, the focus, or sometimes called the hypocenter, that's the actual point of rupture inside the Earth. The epicenter is the term for the point on the surface directly above it.
An important distinction. So the focus is where the bomb goes off, and the epicenter is ground zero on the map.
Perfect analogy.
Now, these waves you mentioned, these are the messengers you're talking about.
These are our probes. We have two main categories, body waves and surface waves. Body waves are the crucial ones for our investigation because they travel through the body of the Earth.
And within body waves, we have the famous P and S waves.
P waves for primary and S waves for secondary. The names just tell you the order they arrive in. P waves are faster, so they're the first signal to hit any seismograph anywhere in the world.
And what is a P wave actually, like physically? How does it move?
Think of a sound wave. It's a compressional wave. It vibrates parallel to the direction it's traveling. Imagine you have a slinky stretched out on a table. If you push one end forward, you see a pulse of compression travel down the slinky. It pushes and pulls the material it's moving through.
Okay, so it squeezes the rock and then stretches it.
Exactly. It creates these little differences in density as it passes. Now, for our detective story, the most critical property of P waves is this. They can travel through solids, liquids, and gases.
Go through everything. Got it. Now for the S waves.
S waves are slower, they arrive second, and their motion is completely different. They're transverse waves. They vibrate perpendicular or, at a right angle to the direction of travel.
Okay, so if the wave is moving forward, the ground is moving.
Up and down or side to side. Think of taking one of those big, heavy battle ropes at the gym and whipping it up and down. The wave energy moves forward, away from you, but the rope itself is moving vertically.
Creating crests and troughs.
Precisely. And here is the absolute key. If you're studying for the UPSC exam, this is the one fact you have to burn into your memory. S waves can only travel through solid materials.
Why is that? What's the physics there?
It's because liquids and gases have no shear strength. You can't shear water. If you try to move it from side to side, it just flows. It doesn't resist and snap back into place. It can't transmit that battle rope motion. So when an S wave hits a liquid, it just stops. It gets absorbed.
Wow. Okay, that is a massive clue. If you send S waves into the Earth and they don't come out the other side...
You know for a fact they must have hit a layer of liquid. Bingo! That's the key that unlocks the structure of the core.
Before we get to what that key unlock, you mentioned a second category of waves, surface waves.
Right. When the P and S body waves travel up and hit the surface, they interact with the surface rocks and generate these new waves that travel along the surface, like ripples on a pond.
And these are the ones that do all the damage.
These are the killers. They're slower, but they have a much larger amplitude, a bigger motion. They are the ones that cause the most displacement and bring buildings down. But for mapping the deep interior, they're not useful. because they don't go deep.
You just skim the top.
Yeah.
Okay, so let's stick with our deep probes, the P and S waves. This brings us to section 3, the shadow zone. This is where the geometry gets really cool. This is the aha moment, isn't it?
This is the definitive proof. It's an absolutely beautiful piece of scientific deduction. So let's imagine an earthquake happens, say, at the North Pole. We have a network of thousands of seismographs all over the planet listening.
Okay, global network is online.
For the first 105 degrees of angular distance from the North Pole, so that's a huge chunk of the northern hemisphere, all the seismograph stations record both P waves and S waves, just as you'd expect. The P wave arrives, then a little later, the S wave arrives.
Okay, so far so good. The Earth is solid down to whatever depth those waves reached.
But then, if you look at the stations located between 105 degrees and 145 degrees away from the epicenter, something bizarre happens. They record nothing.
Nothing. A total dead zone.
A shadow zone. Complete silence. No P waves. No S waves. But then it gets even more interesting. If you go beyond 145 degrees, so now you're on the opposite side of the planet from the quake, the P waves reappear.
They come back.
They do. But the S waves, they never show up again, anywhere beyond 105 degrees.
The S waves are just gone for that whole half of the planet.
Completely. That entire region, from 105 degrees on one side all the way around to 105 degrees on the other, is the S-wave shadow zone. It covers over 40% of the Earth's surface.
And applying our rule from earlier, if the S waves disappear.
It can only mean one thing. There is a massive liquid sphere deep inside the Earth that is physically blocking them from passing through. That layer is the outer core.
That is just brilliant. It's like a planetary scale MRI. The blockage tells you exactly where the liquid is. But why do the P waves disappear in that smaller band between a 105 and 145? You said they can go through liquid.
They can, but waves don't just travel in straight lines when they pass from one medium to another. They refract. They bend. Think about a straw in a glass of water, how it looks bent at the surface.
Right.
It's the same principle. When the P wave hits the much denser liquid core, it slows down and bends sharply inward. That sharp bend causes the waves to be diverted, and they end up missing that specific band on the surface between 105 and 145 degrees.
So the geometry of the shadows tells us two things. The huge S-wave shadow proves the outer core is liquid.
Mm-hmm.
And the smaller P-wave shadow helps us calculate the exact size and depth of that core based on the angle of refraction.
Precisely. That is how we determined, with incredible accuracy, that the core mantle boundary is at a depth of 2,900 kilometers. Not by digging, but by measuring a shadow.
That is a masterclass in deduction. Unbelievable.
Yeah.
Okay, let's quickly touch on section 4, types of earthquakes. We mostly think of the tectonic ones, the big plates slipping, but there are others.
Yes, tectonic earthquakes are the vast majority, but we also have volcanic earthquakes. These are generally smaller and are caused by magma moving and exploding underground as it tries to force its way to the surface. They're confined to areas around active volcanoes.
And then there are the ones, well, the ones we cause, the human-induced ones.
Unfortunately, yes. In big mining regions, you can get what are called collapse earthquakes, where the roof of a huge underground mine shaft fails and collapses.
And explosions, obviously.
Right. Explosion earthquakes from things like nuclear testing. But the most significant ones are reservoir-induced earthquakes.
This is from building massive dams, right?
That's the one. When you build a huge dam and create a massive reservoir, you are putting billions upon billions of tons of water weight onto a very localized area of the crust. That immense pressure can sometimes lubricate existing faults or even fracture the rock, triggering earthquakes.
That's a sobering thought, that our own structures are heavy enough to shake the planet.
It is. The Koina earthquake in India back in the 60s is often cited as a prime example of this.
Wow. Okay, now measuring these things. Richter versus Mercalli. I know I always get these two confused. What's the simple way to remember the difference?
The simplest way I've found is this. Richter measures the cause. Mercalli measures the effect.
Okay, break that down for me.
The Richter scale, or more accurately, the magnitude scale, measures the amount of energy released at the focus. It's an objective, calculated number. A magnitude 6 earthquake is a magnitude 6, whether it happens in a packed city or in the middle of the Antarctic ice sheet.
So it's the size of the explosion itself.
Exactly. And it's logarithmic, which is important. Each whole number up represents a tenfold increase in the measured wave amplitude.
Okay, so Richter is energy. What about Mercalli?
The Mercalli scale measures intensity. It's a subjective observational scale, usually given in Roman numerals from I to 12. It describes the visible damage and what people felt. Did windows rattle? Did chimneys fall? Did all the buildings collapse?
So let's take that magnitude 6 earthquake. If it hits in the middle of the Sahara Desert.
The Richter magnitude is 6. The Mercalli intensity is probably I or I not felt or felt by very few because there's nothing there to damage and no one to feel it.
But if that exact same magnitude 6 earthquake hits the center of a densely populated city.
The Richter is still 6, but the Mercalli intensity could be 7 or 8, very strong or severe, with widespread damage.
Cause versus effect, energy
Yep.
versus destruction. Perfect. That's crystal clear. Okay, section 5. We've done the detective work. We've used the waves. What's the final picture? What is the anatomy of the Earth?
So after all that, we're left with a 3-layer cake, fundamentally. You have the crust, the mantle, and the core.
Let's start at the top with the crust.
The crust is the skin of the apple. It's the outermost solid part, and it's very thin and brittle. But it comes in 2 very different flavors: continental crust and oceanic crust.
What's the difference?
Continental crust is what makes up the land masses, what we're standing on. It's relatively thick, averaging around 30 kilometers, but under major mountain ranges like the Himalayas, it can be pushed down to 70 kilometers thick.
And it's made of lighter rock.
Yes, lighter granitic rocks. Think of it as being kind of thick and buoyant. Then you have the oceanic crust, which is the floor of the oceans. It's much, much thinner, only about 5 kilometers thick on average.
Okay.
But, and this is the key to everything in plate tectonics, it is much denser. It's made of a heavy volcanic rock called basalt.
So a thin but heavy cracker versus a thick but fluffy piece of bread.
That's a great analogy. And because the oceanic crust is denser, when the 2 types of crust collide, the heavy oceanic crust always loses. It always dives under the lighter continental crust. That process is called subduction.
Got it. Okay, so below the crust, we hit the mantle. This is the bulk of the planet, right?
It's about 84% of the Earth's total volume. It's huge. It extends from the bottom of the crust all the way down to a depth of 2,900 kilometers. But we need to make a really critical distinction here. This is probably the #1 thing students get confused about.
Lay it on us.
The difference between the lithosphere and the asthenosphere.
Okay, I have to admit, I always thought the lithosphere was just another word for the crust.
See? It's a super common mistake. The lithosphere is a mechanical layer defined by its strength. It includes the crust plus the very top rigid part of the mantle that's fused to it. It's one solid, rocky slab.
Oh, okay, so the tectonic plate itself is the crust plus that bit of hard upper mantle.
Exactly. Now, below that rigid lithospheric plate is the asthenosphere. Astheno is Greek for wet. It's a layer in the upper mantle down to about 400 kilometers. That is so hot it's not fully solid, it's plastic. It can flow over geologic time like super thick hot tar.
So the hard, rigid lithosphere plates are basically floating and sliding around on top of this soft, gooey asthenosphere.
That is the fundamental mechanism of plate tectonics, and that asthenosphere is also the main source of magma. When a plate cracks, that hot, pressurized, weak rock can rise, decompress, and melt to become the magma that feeds volcanoes.
Got it. So crust plus topmost mantle, which is the hard plate, and below that is the asthenosphere, the soft, flowing layer.
Perfect. And then below the asthenosphere, the pressure becomes so immense that the rest of the lower mantle becomes solid again all the way down until we hit the core.
A core, the knife layer.
Ni for its main components, Ni for nickel, and Fe for ferrous, or iron, the heaviest stuff that sank to the middle.
And as we proved with the shadow zones, the outer core is liquid iron and nickel. But the inner core, right at the center, is solid. Why is that if it's even hotter?
It's all about pressure. The pressure at the very center of the Earth is so astronomical, so crushing, that even at temperatures harder than the surface of the sun, the iron atoms can't break free into a liquid state. They're squeezed together into a solid crystal.
And that spinning liquid outer core flowing around the solid inner core. That's our planetary dynamo, isn't it?
That's it. The movement of that conductive liquid metal generates the Earth's magnetic field. Without that liquid iron ocean spinning down there, we wouldn't have a magnetic shield.
And without the shield.
The solar wind would strip away our atmosphere and our oceans. We'd end up like Mars, a cold, dead rock.
It's amazing how it all connects. The deep geology protects the surface biology.
Yeah.
Okay, section 6. This is where the rubber meets the road for our simplified UPSC listeners. We have the theory, we have the layers, How do we use this information to actually answer questions in the exam?
This is absolutely crucial. UPSC Mains is not going to ask you a simple question like, describe a P wave. That's class 11 stuff. They're going to ask about the geographic consequences of these processes. They want applied knowledge.
Okay, let's take a real one. From the 2020 GS Paper 1, Question 4. Discuss the geophysical characteristics of the Circum-Pacific Zone.
Right. First thing you do is translate. Circum-Pacific Zone is the proper term for the Ring of Fire.
So how do we use Chapter 3 to answer that? You can't just list the countries in the Ring of Fire.
Exactly. That's a weak answer. A strong answer explains why it's a ring of fire. You have to talk about the geophysical characteristics. You bring in the concepts we just discussed. You explain that this zone is where dense oceanic lithosphere is subducting diving under the lighter continental plates.
You use the mechanism.
Yes. You say that because the plate is subducting, it melts in the asthenosphere, and that melting creates the chain of volcanoes. And because the plates are grinding against each other, immense stress builds up and releases, creating frequent, often deep focus, earthquakes. The geophysical characteristic is that dynamic interaction between the crust and mantle.
That's a much more powerful answer. Okay, how about this one from 2013, question 17. Why are the world's fold mountain systems located along the margins of continents? Bring out the association between the global distribution of fold mountains and the earthquakes and volcanoes.
Another classic. Look at the key phrases. Margins of continents. Why there? Because that's the plate boundary. That's where the collision is happening.
The continental car crash.
Exactly. You bring in the fact from the NCERT book that the continental crust is thick, up to 70 kilometers under the Himalayas. Why? Because the collision crumpled and folded the rock like the hood of a car in a crash. The association they're asking you to bring out is that all three things, the mountain building, the shaking from earthquakes, and the melting for volcanoes, are all just different symptoms of the same underlying cause, plate tectonics at the continental margins.
So you link the static fact, like crustal thickness, to the dynamic process of collision. Fantastic. One more from a mock paper for 2025, question 7. What are tsunamis? How and where are they formed? What are their consequences?
This one is a bit of a trap. A lot of students will just write, a tsunami is a big wave caused by an earthquake.
Which is not wrong, but not good enough.
Not for top marks, no. You need to use the specific earthquake concepts from this chapter. A tsunami is generated by a vertical displacement of the ocean floor. You must state that the focus of the earthquake has to be under the ocean, making the epicenter a point on the seabed.
And the magnitude matters, doesn't it?
Absolutely. It generally needs to be a powerful quake over magnitude 6 or 7 to displace a significant volume of water. The best answers will explain the energy transfer. The energy released at the focus creates a fault slip that lifts the entire column of water above it, giving it huge potential energy. That potential energy then propagates outwards as the tsunami wave.
So it's not just a wave, it's the movement of the entire ocean column.
If you explain that energy transfer from the lithosphere to the hydrosphere, you're showing a deep understanding. That's the key. The static facts are the bricks, but the answer you write is the house you build with them.
What a journey. We have covered a massive amount of ground, literally, from that 12-kilometer scratch at the Kola borehole all the way down to the 6,000-kilometer deep iron heart of our planet.
We've seen how a simple shadow can reveal a liquid core, and how a layer called the weak sphere, the asthenosphere, is actually the powerhouse that moves entire continents.
I will leave our listeners with a final thought, something the book touches on right at the end. It mentions this constant battle between exogenic forces like wind and rain that wear the land down, and endogenic forces like volcanoes and uplift that build it up.
The eternal struggle. Construction versus destruction.
Right. And those endogenic forces, the builders, are all powered by the Earth's internal heat. Heat left over from its formation and heat from the decay of radioactive elements.
Yes, sir.
That's a finite fuel source.
It is. The Earth is cooling down, incredibly slowly, but it is cooling.
So what if the engine stops? If the core eventually solidifies completely and the mantle cools?
Then the endogenic forces would cease. No more plate tectonics, no more earthquakes, no more volcanoes, no more new mountains being built.
But the exogenic forces would keep going. The sun would still shine, the wind would still blow, the rain would still fall.
And eventually they would win. With no force building things back up, erosion would grind every mountain down to sea level. The sediments would fill the oceans. The planet would become a flat, featureless, geologically dead world.
Like Mars. That is a terrifying and also kind of beautiful thought. The very forces that scare us, the earthquakes and volcanoes that can be so destructive, they are literally the heartbeat of a living planet.
Without the chaos, we wouldn't have the home.
On that note, we are wrapping up today's deep dive into the Earth's interior.
It's been a real pleasure exploring the depths with you today.
And before you all go, just a quick reminder, if this helped you visualize the invisible world beneath your feet, please take a second to subscribe to Simplified UPSC by PPP. We're building a community of deep learners here, and we'd love for you to be a part of it.
And if you're able to, please do consider supporting us on Patreon. It allows us to dive deeper, research harder, and create better content like this. And a huge final thank you to all our current supporters.
Absolutely. Don't forget, the free notes and the PYQs are on the public Telegram channel. But if you want that premium experience, the organized library of all the videos, the detailed notes, the model mains answers, you need to join the private Telegram library.
Just DM us on the public channel to get access. And please, like the video, share your comments, let us know what mystery you want us to decode next.
Until then, keep digging, keep learning, and stay curious.